Hello, my name is Bob D. Hilster, and I am your particle model guru. Today I'm going to start a series of one or two, maybe more videos on light. And today it will be on reflection and refraction. But first let me report, since my last video I just gave a short video saying I was attending a conference, the 2018 CNPS conference. That's the Chappell Natural Philosophy Society. It's named after John Chappell, who was the founder of this society, and we're naming it after him in his honor. I'm back from the conference, obviously, and all the talks were live streamed and can still be seen, but if you click on, you have to log into youtube.naturalphilosophy.org. When I was there, I gave a paper, and I wrote a paper titled Dark Matter versus G, and I gave a talk, and the link here below is a direct link to that video. This is based on my particle.guru talk of the same title, which I gave quite a while ago. In fact, it was even last year. In this video, I explain about the same thing, but there is some interesting discussion following that presentation. And so this will be a series of videos, today reflection and refraction, to dispersion, and dispersion may be broken up into pieces. It's not an easy subject, it takes some time. But first I have a question. How many? How many reflections, how many refractions, how many dispersions are in this drawing? It's not an actual photograph, this is a drawing. And where do they occur? Well, I don't have them labeled on the picture, and I apologize, but I'm going to call them points A through F. And starting on the left side, left bottom is A, B, C, D, E, and F. Just to help you, B is the source of the white light. Question is how many? Next time I will give you my answer, and if any of you choose to respond, send me yours. How many reflections, refraction, and dispersions do you see in that drawing? Okay, well, all three of them are shown in this drawing one way or another. You have incident white light, where you're coming presumably from air into a glass. Yeah, here it is, air into glass. And the white light is reflected this way, and the reflected angle is measured from a vertical normal, which is theta 1. And the angle of incidence equals the angle of reflection. That's pretty simple, straightforward. Refraction is shown because as refraction shows the light coming here and bending, and that's refraction. And if you have blue light, it'll bend this much. If you have red light, it'll bend this much. But if you have white light, you get both and all of them in between and around those two lens. So dispersion is, dispersion is with white light. And you get the rainbow effect. Those are all three shown here in one picture: reflection, refraction, dispersion. So let's talk about reflection. Reflection from a mirror. We're all quite familiar with that, and my assumption is that the surface of the mirror is flat. Whatever the glass molecules are, and molecules and atoms are, that they are well ordered. Reflection from a wall is not necessarily, it is reflection, but I use a more unique, more specific term, scattering, because the wall does not reproduce a image. So let's take a look at that. A mirror scatters and maintains an image. Now, you may not think a mirror scatters, but let's look at it for a moment. So I'm standing back here. This is my face. Of course, my face is over to the right, but I'm assuming my face is here, and the ambient light hits my face and scatters off of my face, just like it scatters off of a wall, and it comes, one point of my face comes to this particular molecule or atom, probably the nucleus. I'm not sure. I'm giving you my opinion here, that if the nucleus is round, this would help give a good image back. Now, it scatters, but in one of these can go straight back to my own face, so I can see my image. But as this same point has a stream of light coming this way, it could go off in that direction, this direction, both horizontally and vertically. Now, the reason it scatters is that if you were standing over here and you looked in the mirror, you could see my face, and the only way you can do that is if this image scatters in this direction. If you were standing over here, the same thing. the light has to scatter in that direction, and you can stand behind me and see the same image that I do, or similar. It scatters, but it maintains the image because the group of points coming off my face to any number of groups of particles or atoms or nuclei all come out back, give a coherent set this direction, a coherent set this direction, a coherent set, and that's the function of the surface of the mirror. It might tell us something about that surface. Now, from a wall, however, where the wall is not so smooth, the wall scatters and my face image is lost. I can be standing in front of a wall, ambient light hits my face, the points off of my face come hit the wall, and this is the same one as I showed with the line going straight back and this way. Just coincidentally the same as I showed in the mirror, but this one is different because of where the location is. It's further down and around. It's going to scatter in a different way, and my face image is lost. But I also want to make the point that you point a red laser at the wall. That image is scattered, but the image is not lost. Of course, with the red light, you have a concentrated point, or circle, if you will, on the wall where the high intensity red laser is painting all of that wall red and scattering in all directions. It has to be, you can see it as a dot, and so there's enough light, there's so much light coming that all the scattering, even though it scatters in what appears to be non-coherent way, enough of those images hit your eye that you can see it. It has to do with the intensity. It's reflection. Both the mirror and this one are reflection, but there is scattering at the same time. We tend to think of reflection as angle in, angle out. Scattering is angle in. It has a different angle out. Okay, so what about refraction? Let's read about refraction in Wikipedia, my favorite source for finding problems in how they describe things. And refraction is the change in direction of a wave propagation due to a change in its transmission medium. And that's generally true. excuse me. But then they go on to explain it. Okay, the phenomena explained by the conservation of energy and the conservation of momentum. When I read a sentence like that, it gets my attention because I'm of the opinion that conservation statements, whether it's energy, momentum, or something else, is not an explanation. It's not a cause. It's an effect. In other words, if you define a system and it's well defined and you account for all properties of, or what's going on in that system and event, you need to explain what's happening in terms of physics. Not that conservation isn't part of physics, but you need to explain it. And as a result, if you explain it correctly, you can show that there is conservation of energy or momentum. It's kind of a rule. I listened to someone talk, and if in the end I can see his explanation doesn't conserve energy or momentum, then I might say, well, his system is not well defined or not well explained. You use the physics to explain it, and you justify it using the conservation of energy or momentum. Anyway, back to the point. Owing to the change of medium, the phase velocity of the wave has changed, but its frequency remains constant. The phase velocity, the velocity of the phase remains constant, but the the phase velocity changed, but the frequency remains constant. Now, in general, I'm going to be talking about light leaving air and entering glass. And in that case, it slows down. When it leaves glass and enters air, it speeds up, and we can talk about that, but for the moment, I'm going to say it appears to slow down. Because when they measure the propagation delay of the light, measuring from peak to peak, then they see that the time has increased. Whether it's red, green, blue, or any other color, the time has increased for it to propagate through the glass. Now, they're saying that the frequency is constant, the time increases, c is a constant, and therefore the phase velocity goes down. That's an equation that represents this idea. Now, to me, frequency is not real, and I'm more in tune with the wavelength, and so I've rewritten this equation. It's a valid conversion from here to here, and you get this same result, except in my case, I would say the wavelength stays constant. The wavelength going in and the wavelength coming out is the same. So they use this slowdown to try to explain it. It's all about the slowdown of phase velocity. And so what they do is they use the idea of marching soldiers. Now, I got this picture. I kind of like the picture, but you're going to, where I got it is rather unusual. The nakedscientist.com, Get Naked Experiments, Making Pyrex Invisible, was the link to where I got this picture. Anyway, that's not the point. However, what you have are 4 columns of marching soldiers, all marching at the same speed, but when they're marching on hard tarmac, is what they usually say, and they hit sand or mud. And this first column reaches first, and there's the first mistake. Light is bent as it hits. No one usually says it goes straight for a while and then turns. That's what happens in this drawing. Here it goes a little bit in as well. Finally, you have one turning at both of these turning at the surface. But what happens is this guy automatically slows down because it's sand. He's going slower. He can't help himself. He's going slower. This guy's going faster. And in order for these guys to line up properly as soldiers, in a sense, you can think of him waiting for this guy to catch up and this guy to catch up and so on. And they're off marching in 4 columns and lined up properly in rows. Well, it all depends on whether you're talking, sometimes if you talk about a wave, that might actually seem pretty straightforward. When you talk about a particle, that doesn't work. Particle model for light. If you think of these as photons or just a particle, excuse me, as a particle, it doesn't look over to the left to see where the other one is and go on. The title of this one, by the way, Making Pyrex Invisible, they suggest in the article that you take a Pyrex bowl and push it down into a larger bowl with vegetable oil, and it disappears. It's like magic. Well, the explanation in this case is that the vegetable oil and the Pyrex glass happen to have the same index of refraction, and hence there is no refraction. It goes straight through like it wasn't there. Just an interesting side comment. Okay, so let's go to the particle model. At this point, I recommend that you watch my video titled Two Gravities. This is where I use the particle model of light to suggest that there are 2 gravities. In other words, there's a point at which I looked at refraction and concluded there's a second gravity. Now I'm going to use the second gravity to explain how it refracts. It almost seems circular in logic, but you can view this video, YouTube video that I made, going to that particular link. Well, this is a slide from that video, and what I showed was this block and this laser light with no arrows, and then the next one I showed 1 arrow, and I said that what if there was a force, or what kind of force and what direction would that force have to be to cause this light to bend that way, and I drew that line. Then later I drew that line, and it was at that point that when I looked at this and this, I said, wow, I've seen this before. That looks very much like Newtonian gravity. Well, later on in that video, I showed the fact that, well, there really aren't, you can see or visibly, they're not quite, they don't quite behave the same at all, but similar. There's forces all around the Earth and all around. And so I said there must be a gravity 1, that's a Newtonian gravity, and a gravity 2 that bends light. And we shortened gravity 1 down to its nickname G1, G2. So that's what the video explains. And this was done just after I had claimed that the particle model for light is a wave of particles moving at speed c with a repetitive distribution. Peaks here, peaks there, valleys here, and this repeats and repeats. To me, the wavelength is real. The frequency isn't real, because in order to get the frequency, you have to take and do the math of wavelength, and with wavelength and the speed of light, whatever the speed is. So it's a stream of particles. So here we have a G2 force around a prism, and the prism could be made of glass, which we already talked about, so presume that it's smooth. And you have the streams of G1 particles coming this way and streams coming this way, and the vertical G2 force this way. What's interesting to note is that this vertical force can be broken into 2 components. You go from the tail of this force vector perpendicular to the light, and then you go from the point of this one to the the point of that one as a second vector. This vector component, this component of force, causes the light to turn, but this one causes it to accelerate. So in the particle model, it not only turns, but the G1 particles go faster as they come toward and enter and turn. Now in reflection, reflection and scattering happens when the light hits the atom and bounces off in either a well-ordered direction for the image, or scattered direction so you can have multiple images. But in the case of the light going through the prism, there's a large portion of the light that goes right through the gap and proceeds on through the prism. So actually you can have all three happening at one time. You can have reflection, refraction, and going through and later on dispersion. You can have all these things happening all the time. Some part of the light reflects, some part refracts, some part goes through. So this is the analysis of the force and how it causes it to bend. And this is gravitational, which means that the force is weaker as you go out, so it may even start bending sooner. And it doesn't look that way, but of course we're talking about light which has a wavelength of nanometers, and blue light or red light is between 400 and 750 nanometer wavelengths. These are very small wavelengths that we're talking about. Anyway, that's how I explain refraction using the particle model. No marching soldiers. Slowing down. I mentioned that it appears to slow down. And I'm going to make one more point while I'm here, and that is this stream of particles moving at speed is moving faster, not slowing down. And as it goes through, it does, although it appears to us to go as a straight path, may not go through as a straight path. It may zigzag through there. If you get down at the size of the G1 particle, it may be zigzagging, but its net flow at the end is virtually straight. But the speed doesn't slow down because this is open space. There's particle model, we're saying that there's open space between atoms and molecules. There's nothing there to slow it down except more G1, G2 particles that happen to be flowing through. So yeah, there is another order of effect, but basically it speeds up going into, when it gets to about a halfway point, some medium point, it starts speeding. It starts slowing down. It speeds up here going in. It speeds up. It slows down going out. Okay, angle of incidence. There is a critical angle at which some of these things happen. This is just a side issue. As long if you're normal, if you put the light in straight in, you say, well, where's the reflection? Well, yeah, it'll reflect straight back at you. There is no refraction because the light goes straight through. If it's at some angle between here and the normal and the critical angle, it'll reflect and it will refract. You get lower than that, there's a point at which, and they don't talk about this much, where there is only reflection. The light doesn't go through, it just bounces off and goes off into space because it can't bend fast enough to get into the open spaces of the glass. Oh, so here's my conclusion. The standard explanation, light slows down when it enters the prism, and it turns like columns of marching soldiers, marching from tarmac to sand. Beautiful explanation, excuse me. The particle model says that light speeds up before it gets to the prism. The G2 net force turns. One vector of the G2 force turns it. Another vector accelerates it as it goes in. Light, on the other hand, turns and slows down when exiting the prism. Although the average speed, by the way, and I didn't get to that point, the average speed through the glass, the speed of the average is about the same in my model. It appears to be a delay, a slowing down, because it doesn't take a straight path. And I forgot to mention that there. Anyway, my name is Bob D. Helster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.